Hi, my name is Summers Pittman. I am a software engineer at Red Hat, and this is my talk, Java Records in a Flash. Java Records are a newer feature available in Java 16 and have been in preview since Java 14. If you want to know more beyond what is in this talk, I recommend you check out JEP 395 and the Amber mailing list. These resources cover records and their design in much more detail than I can in 10 minutes. This is a lightning talk after all. Records are a whole class in as little as one line of code, which define a named tuple with immutable data. In this example, we define a record point with fields x and y. Java implements for us equals, hashcode, toString, accessors, and a canonical constructor with the method fields as parameters. Records do have some restrictions that don't apply to normal classes. Records are immutable, aren't allowed to have instance fields other than the record parameters, may not inherit from other classes, nor be extended by other classes. Fields are private and must be accessed through accessors, and serialization cannot be customized. JEP 395 covers these restrictions in more detail. Otherwise, records behave as normal classes. You can instantiate them with new, print them with toString, compare them with equals, use them as keys for maps, etc. Because the JVM implements equals and hashcode, you get a lot more reliability when using records as map keys. In this example, we create 5,000 record instances which have 256 unique values and use them as keys in a map. A traditional class implementation's default hashcode and equals method would create a map with 5,000 unique entries, but the record implementation correctly only creates 256 entries. Another feature of records is that their parameter names are encoded in their bytecode. This lets tools such as Jackson use records to marshal and unmarshal JSON data without bean pattern accessors, field annotations, or constructor annotations. In this example, our point class is passed to the Jackson object mapper, which reads in point data in JSON format and transforms the JSON file into point objects. We then stream this data out and print it using the generated toString method. It is worth repeating just how much code you actually have to write to do this correctly in Java. Where our record point requires a single line, a classical equivalent to it won't even fit on a slide. While we can use an IDE to generate most of these methods, it is very easy to introduce subtle bugs into our code. For example, if we add a field to the class, we would have to remember to regenerate all of our generated methods. A record implementation has these methods regenerated automatically. Records can be declared locally inside of a function. In this example from JEP 395, we are sorting our merchants by the number of sales they've had in a month. We define a local merchant sales record with a pair of values, the merchant and their monthly sales. This method maps the merchant instances from the merchant's parameter into merchant sales records using the generated canonical constructor. Our stream sorts these record instances by sales, extracts the merchants, and then returns them in a sorted list. The benefit of this is that we haven't created an extra class file, and the overall code is cleaner than if we had used traditional classes. Records support generics as well. Here we have an example of a simple pair that accepts any two values. These values can be accessed by using the methods first and second. This pair can be used as a key in a map, marshaled to JSON, printed, etc., all in one line of code. If you have a situation where a method needs to return multiple values in one object, then a record may be more useful than creating a class. For example, in the Go language, it is a common pattern to return a pair of values, with the first being the result of a function and the second being an error, if any. The Go program then checks if the error value is defined, and if so, handles the error. In Java with records, we can recreate this pattern with a record class holding two generic parameters, a value generic type of any object and an error generic type bounded by the exception. In the example shown, we read a file and return a record with string and null if the file is read successfully, and null and the exception in the case of an error. This is useful if throwing an error in an exception isn't an appropriate action and we don't want to lose the exception that occurred, or if we are porting Go code to Java and don't want to refactor the logic yet. Records also introduce a new type of constructor, the compact constructor. A compact constructor implicitly has parameters which match the record parameters. The compact constructor's parameters are automatically assigned to the record parameters at the end of the constructor body. This is useful if we are validating or normalizing inputs. In this example, our compact constructor is enforcing not null and type requirements on our x and y parameters. In this example, instead of throwing an exception, we are setting a maximum value for our record parameters. This color record represents a 24-bit RGB color value with 3 int parameters, R, G, and B. In this color format, the maximum value of any single color parameter is 255. We've created a compact constructor that is giving the RGB parameters and clamps them to 255. After this block is executed, Java assigns these parameters to the records R, G, and B fields respectively. Records can still have more traditional constructors. They must set the record fields or delegate to a constructor which does so, as is the case with final fields in traditional classes. In this example, we've created a constructor that doesn't consume 2 parameters like the canonical constructor, but instead requires a map.entry value. It destructures the entry into its key and value and assigns them to the first and second parameters respectively. We can then use the Streams API to transform a map class into a list of its pair values. Records generate accessor methods on their fields automatically. Record fields are private, and your users will only be able to access them via accessor methods. These are named following the pattern field name and parenthesis. Importantly, they do not follow the bean pattern of get plus field name then parenthesis. We can still override them as if they were traditional methods, and this lets us log access, modify the return value the user sees, and so on. In this example, the first accessor method logs it to the standard out with the message first accessed. If you change the value your accessor returns, then you might also need to override the equals and hashcode methods, as your users might expect different behavior than they get if you've returned different values. Records can also have instance methods. They aren't allowed to change the record fields, but they are useful for performing transformative operations on the record data. Here we've implemented a method that merges 2 pairs into a pair with 2 lists. Other use cases for instance methods on records would be mathematical operations. For example, the big decimal APIs have an add method which combines 2 immutable big decimal objects into a new big decimal object with the sum of its 2 parts. Records are going to be developed in Java as the language evolves. In JEP 405 and 409, we have previews of 2 features that are discussed. The first is destructuring a record using Java's new instance of pattern matching. The block following the pattern match can use the record's parameters directly, as we see here with the radius of a circle record instance. Additionally, records will be able to act as sealed classes. Sealed classes let developers define the set of all implementations of an interface. Because the compiler will know how many implementations exist, future versions of Java will be able to confirm that adding implementations of classes won't break legacy code at compile time. Records can be the data holders, and default methods on the interface can safely provide comprehensive implementations. In this example, we have defined a shape interface, 3 record implementations, and a default method to calculate the area based on the type of shape. If we add a new shape record interface to the interface, the switch statement will fail to compile until we've added in that case for our new shape. Thank you all for listening. Again, if you want to know more about records, JEP 395 is an amazing resource. If you want to know more about me, follow my GitHub at Second Son or my Twitter at Summers Pittman. Have a great night, and thank you, AJUG, for hosting this talk.